take a look at exercise 61 from section 1.5, where we consider solving a quadratic equation by completing the square.
Let's look at solving this equation. The first thing I'm going to do is get the constant on the right side of the equation by adding 1 to both sides of the equation. So the equation becomes 7x squared minus 7x equals 1. My next step is to divide by the coefficient of x squared, which we call that a, if a is not 1. So a is 7, so I divide every term of the equation by 7. And I obtain x squared minus x equals 1/7. I have to understand that there's really a 1 in front of x. So the coefficient of x is minus 1. I take half of that and square it and add this to both sides of the equation. Notice I'm ignoring the minus sign because that will get absorbed in the process of squaring. So I now have x squared minus x plus the square of 1/2 on the left and 1/7 plus 1/4 on the right. So on the right, I go ahead and square the 1/2, which is 1/2 times 1/2, or 1/4. The left is now a perfect square trinomial, which factors into the square of x minus 1/2. On the right, I have two fractions with different denominators that I need to add. So I find a common denominator, which happens to be 28. I multiply 1/7 by 1 in the form of 4 over 4, and I multiply 1/4 times 1 in the form of 7 over 7, so that these both become fractions whose denominator is the same, and that is 28. So 4 over 28 plus 7 over 28 is 11 over 28. So I'm now going to apply the square root property. I lose the power of 2 on the left by applying plus or minus square root to the 11 over 28 on the right. And square root of 11 over 28, using the quotient rule of radicals, can be written as the square root of 11 over the square root of 28, which I need to rationalize the denominator.
Okay, so in rationalizing the denominator, we pick the smallest number that we can multiply 28 by so that 28 becomes a perfect square. So the perfect squares are found by starting with the integer 2, squaring it. So my smallest perfect square is 4. Then I square 3, and I get 9. Then I square 4, and I get 16. So forth and so on. All the way up to, if I square 14, I get 196. So that's the smallest number that 28 divides into evenly. That's a perfect square. And 28 divides evenly into 196 7 times. So I multiply the numerator and denominator by 1 in the form of square root of 7 over square root of 7, so that the denominator becomes the square root of a perfect square. So on the left, I still have x minus 1/2. Now on the right, I have plus or minus square root of 11 times square root of 7. The product rule for radicals tells me that's the square root of 77. The square root of 28 times the square root of 7 is in the denominator, and the product property of radicals tells me that's the square root of 196. So notice when I have real numbers that are radicals, and I'm multiplying radicals times each other, they have to have the same index. These are both square roots, so they both have an index of 2. So I'm multiplying within the square root 11 times 7 in the numerator. And in the denominator within the square root, I'm multiplying 28 times 7. So I now have x minus 1/2 on the left, and I have plus or minus square root of 77 over the square root of 196 on the right. The square root of 196 is 14. So I have x minus 1/2 equals plus or minus square root of 77 over 14. And then to solve for x, I add 1/2 to both sides of the equation. So x is 1/2 plus or minus the square root of 77 over 14. So in my math lab, the problem already has the solution set is for you, as well as the set of braces, and you have to put in the two values of x that make this equation true. One value is 1/2 minus the square root of 77 over 14. I separate that from the other value with a comma, and the other value is 1/2 plus the square root of 77 over 14. And that's my solution and how I obtain it.